In the today lesson, we will discuss about the coordinates, bases, and dimensions. So this is the important topic regarding the continuation of the elements of a vector space. Basically, we before we saw that the spanning set and also the linearly independent set, like the which set span some space and which of the set is linearly independent set. And in the basis is actually the continuation of that one. If a set is independent as well as the spanning the entire vector space, then that set will becomes a basis of the same vector space. Okay, let's go start with that one. So first of all, the coordinate vectors. Look at the coordinate vector is actually related with some coordinate elements. And here there are the first we will recall the definition of a basis set. If V is a vector space and S is a set having some vectors v1, v2 up to vn. This is a finite set of vectors in V. Then this set S is called a basis set for a vector space V if it satisfies these two conditions, that this set is linearly independent. Like whenever you write as a linear combination is equal to 0, then all of its constants must be equal to 0 only. And the second thing is that this set S span the whole vector space V. Like this, the S spans V and S is the linearly independent set. If the set S has these two qualities, then this set S will becomes the basis of a vector space V. And here I also want to tell you something important, that if S is the basis, then the number of elements in set S is called the dimension of a vector space V. For instance, here this set S has a n element in the basis set. It means the dimension of a vector space V is n. So here we can see the standard basis of Rn, like E1, if we take 1, 0, 0 up to so on, and E2 is 0, 1, 0, 0, and En is 0, 0, 0 up to last entry is 1. These are the n tuples vectors. And if you will write as a linear combination equal to 0, then all the k1, k2, k3 up to kn must be equal to 0 only. And this E1, E2, En can span the entire vector space Rn. Means with the help of a linear combination of these vectors, we can generate the whole space Rn. So we conclude from this we conclude that these E1, E2 up to En are the basis of vector space Rn. Similarly, in R3, the vector I, which is 100j, which is 010k, 011, is a basis of this is a standard basis of R3. And similarly, the standard basis of a Pn is actually 1x x square xn. Look, in the basis, there is important thing that all these are independent, like no one is interrelated with the other one. For instance, with 1 and x, we cannot generate x square. Similarly, with x and x square, we cannot generate x3 or x4 or xn or x1. So all are independent to each other. And moreover, these are independent to each other. For instance, like they can, the next thing is that with the help of these, we can generate any polynomial, and these are sufficient that if there is not any other vector, then it will becomes a linearly independent, because all are independent, and with the linear combination of these one, we can generate the all polynomials of degree n. That means it's generate the vector space Pn. So that's why these are the standard bases. Here there is a question arising that if someone wants to check that is the given set is a basis of a Pn or not. So we need to apply the two things, that we need to check that is the given set is or is the given set S is linearly independent or not. And secondly, we need to check that is this set S span the whole vector space Pn. And this test we apply for all the vector spaces whenever the question arises, that check whether the given set is a vector space or not. And for instance, here we have a one. collection of a three vectors like v1, v2, v3. So the question arises that show that it's a vector space or determine its vector space or not. These vectors are a basis of R3 or not. So in that cases, we need to apply the two things that first need to check that is the given set is linearly dependent or independent. If this is independent, then we need also to check that is this span the any vector of R3 or not. If it span every vector of R3, then it means this V1, V2, V3s are the basis of a R3. So these two conditions must be satisfied. But in case if we check the first condition where V1, V2, V3 will become linearly dependent, then we should stop it and we can conclude that these V1, V2, V3s are not the basis of R3. And remember that for any vector space, there can be too many uh, vectors, too many basis sets like 1001, like they are bases, and there are so many elements that can be basis of that one. So we remember in the last lesson that how to check the linearly independence, like we need to write it uh, as a linear combination with the zero vector and then find a solution of this a homogeneous system. And if the C1, C2, C3 is only the zero solution, then it means that these are independent. And also if we write C1, V1 plus C2, V2 plus C3, V3 is equal to some vector B in R3, then we need to apply any method to solve this linear system for the values of a C1, C2, and C3. And if we get this value C1, C2, C3, any value exists, then it means they are spanning the vector space R3. And here there is also one good method, like if we write as a metric A here, it's the coefficient metric, and whenever we apply the elementary row operation, or if we take determinant of that, if determinant is non-zero, it means C1, C2, C3 have a unique solution. If the solution is, then it means every element like B1, B2, B3, we can generate with the help of C1, C2, C3. And this is the guarantee that this the V1, the given vector V1, V2, V3 spans the entire vector space R3. Similarly, there is a question arises that the standard basis of M cross N. For example, if we have a 2 cross 2 matrices, then we have a set of standard bases, which is like M1 if we take 1, 0, 0, 0, M2 is 0, 1, 0, 0, M3 is 0, 0, 1, 0, M4 is 0, 0, 0, 1. And these are the standard bases, and we can check it that they are linearly independent. For instance, if we write C1 M1 plus C2 M2 plus C3 M3 plus C4 M4 is a zero. This means zero metric, like 0, 0, 0, 0 metric, and need to solve it. And also solve it the values of a C1, C2, C3, C4. If the values of C1, C2, C3, C4 is only the zeros, then it means M1, M2, M3, M4s are independent vectors, are independent matrices. And again, we need to apply the spanning test that can this M1, M2, M3, M4 span the every vector, uh, every metric B of a 2 cross 2 matrices. It means that M1, M2, M3, M4 spans the collection of all 2 cross 2 matrices. For this, we just write as a C1 M1 plus C2 M2 plus C3 M3 plus C4 M4 is equal to the any metric A, B, C, D. And then we need to find the solution. If we get the solution like C1, C2, C3, C4 equal to 0, it means that all the given M1, M2, M3, M4s are independent. And if the value on the other case, if as we saw that C1 equal to A, C2 is B, C3 is C, C4 is D, it means that uh, the V1, the M1, M2, M3, M4 generates the all kind of 2 cross 2 matrices. It's mean the M1, M2, M3 span the entire 2 cross 2 matrices class. And it means that if they are independent and span every 2 cross 2 matrices, then we conclude that the M1, M2, M3, M4 is the basis of a all 2 cross 2 matrices like M2 cross 2. And similarly, if we take the standard entries like M1 is only the first entry is 1, in N2 is the second entry is 1 of that class, then they will become the standard basis of all M cross N, where M, whatever the value of small m and whatever the value of small n. Uh, Similarly, here we have some examples for that one, and there are some relations and results. For instance, a uniqueness of a basis representation. If S is a V1, V2 up to Vn is the basis for a vector space V, then every vector V in V can be expressed as a V is equal to C1, V1 plus C2, V2 plus Cn, V1 in exactly one way. Like there is a only unique representation for each vector V with the help of a C1, C2, C3 up to Cn. Like there is not possible that we can get the two different constants C1, C2 up to Cn for any given vector. So if they are a basis, then it always have a unique representation. And another important thing is about the coordinate vectors. Like if S is a basis set, and if we write V as a C1, V1 plus C2, V2 up to Cn, Vn, which means that this vector we write as a express as a linear combination of the vector V1, V2, Vn up to Vn. Then if we combine the scalars C1, C2 up to Cn and put it in a single form of a vector, then this vector is called a coordinate vector of the given vector V. And this coordinate vector we normally denote with the Vs. Like if V is available, V is any vector, then the Vs we can obtain by the coefficient C1, C2 up to Cn. So this is called the coordinate vector. And for any matrices or any vector, we can find its coordinate vector with the help of its basis set. And there are some examples and results are available for that one. For instance, if we saw the example 9, like V1, V2, V3s are available. These are the, suppose these are the bases of R3. We know the basis means they are independent and span every vector of R3. Then find the coordinate vector of 5, -1, and 9. How to find it? Just take V as a C1, V1, C2, V2, and C3, V3, and then need to find the values of a C1, C2, C3. And if we write C1, C2, C3 as a vector form, like first component is C1, second vector is C2, third component is C3, then that vector is called the coordinate vector of V and denoted as a Vs. And look as a if we take V is equal to V1, C1, V1 plus C2, V2 plus C3, V3, then it will become in that form. We know the if we write this as a matrix form and need to find the values of a C1, C2, C3, then by solving with the help of any method, either we use Cramer rule or elementary row operations, or by eliminating rows, or whatever the method we need to solve, we can get the values of a C1 is 1, C2 is -1, C3 is 2. Then the coordinate vector will becomes the C1, C2, and C3 means 1, -1, and 2. So this is the method to find the coordinate vector, and also find the vector V whose coordinate vectors are Vs, like -1, 3, and 2. If we know the basis and we have the coordinate vector like -1, 3, and 2, then we can find the original vector V with the help of that. Just need to write as a C1, V1 plus C2, V2 plus C3, V3, where C1 you just put -1, C2 need to put 3, and C2 need to put 2. And when you solve this linear combination, then we will get the vector v. For instance, here you can see that v is equal to c1 v1 plus c2 v2 plus c3 v3. After addition or just make simplifying that, we can get the vector v, which is 11, 31, and 7. So these are the results about that one. So here I have also some results for you, which we can see about the basis and its and some there some questions arising over here, which we can discuss. Okay, now a collection S having v1, v2 up to vr of a vectors of vectors from the vector space V is set to the basis of V if S is a linearly independent and S spans the V. And there is a question arising in that one, suppose V1, V2, V3, V4 is a basis of V. Like if we have a basis, then prove that V1 plus V2 and the second vector is V2 plus V3 and the third vector is v3 plus v4, and then the v4 is also the basis of a v. Means here there is some addition combination of that one is also the basis. We know the sum of two vectors is a vector, like v1 plus v2 is also a vector. So whatever they are basis, then it's such kind of a combination will also becomes a basis. So for this, what we need to do is we need to show the two things that this collection is linearly independent and this collection spans the this vector space V. First, we need to check that is it's linear, all these linearly independent or not. For this, suppose that A, B, C, D's are the any real numbers such that A times V1 plus V2 plus B times V2 plus V3 plus C times V3 plus V4 plus D times V4 is equal to the 0. This 0 is a vector, and then we need to find the values of a A, B, C, D. So we know that if we can split that V1 take as a common V2, V3, V4, then we can get its coefficients. And since the right hand side is equal to 0, it means that all these coefficients are equal to the 0. And if we solve it, these equation A is equal to 0 put over here, then it means 0 plus B is also 0, which means B equal to 0. If B is 0, then put 0 plus C equal to 0, it means C equal to 0. And if C plus D is equal to 0, where C is 0, then it means D is equal to 0. Hence, it gives that A, B, C, D all are 0. Then we conclude that this V1 plus V2 and V2 plus V3 and V3 plus V4 and V4 is V4. These vectors are linearly independent, or this is the independent set. Now, need to show that this also spans V4, where V1, V2, V3, 4 spans V, capital vector space V. Now, for this, just take any vector as a form of a U is a vector and just write as a linear combination of a1 v1 plus a2 v2 plus a3 v3 plus a4 plus uh, if you say U is equal to AV1 plus BV2 plus CV3 plus DV4, and then with the help of that, it implies U is equal to A. One can write this thing in this form. It's not be the difficult. Like if you take a common and get their common entries with the help of that relations. So which shows that the any vector U can be write as a linear combination of V1 plus V2, V2 plus V3, V3 plus V4, and with V4. So it means V1 like this collection spanning the vector space V. Now, as it's linearly independent and span the whole vector space, it means these vectors are these vectors is a basis, or this collection is a basis of a vector space V. In the next problem, it's important that find the basis of a row space of A. The row space, the row space is a vector space because rows can generate any kind of a uh, vector space. So this itself becomes a vector space. Now, how to find the basis of a row space. We need to apply the elementary row operation and then need to check that how many rows are independent or how many rows are non-zeros after applying the elementary row operation. If we apply the elementary row operation, then we can see that in the first step, if we apply as we have a leading one, then apply the R1 minus R2, it will become the first element will become 0. Similarly, R3 plus R1, if you apply over here, then it will become 0. The next thing is that since we have a leading one, we can use again the elementary operation that apply it and in the R3 and in R1. Since in R1 we have already 0, so just need to add R3 plus R2, then the entire last row will become 0. It means the first two rows are sufficient to generate the third row. It means the only first and second rows are independent because it's already in now echelon form. Like it cannot be further reduced by elementary row operation. Then it means that the only two rows are independent and they are spanning this kind of a all matrices. So hence we conclude that the first row and second rows are the basis of a vector space or a basis of a row space because row space is a vector space. So this is very important that the number of non-zero rows, which is also called the rank. Rank mean number of non-zero rows in elementary form. So here we can see that as the first two rows are non-zero, we conclude that these rows are the basis set of the row space. And in addition, we can see that if we add first vector of basis set into the second vector and then we get a new basis, that is also the basis of a vector space. So this will give us important information that if V1, V2s are the basis of any vector space, then V1, comma AV1 plus BV2 for any values of A and B is also a basis set of the same vector space for any real numbers A and B. So it means the linear combinations of a vector of a basis set is also a basis set. Now there is another important question arises: the find the basis of a null space means solution space of a homogeneous system. Null space is the solution space of a homogeneous system which is Ax equal to B, where A is a matrix available over here. For this, what we need to do is we just need to apply the elementary row operation over there and then need to check that how many rows are independent and independent or how many rows are non-zeros. Like if an elementary row operation is a very important method, it always tells us that how many rows are independent to each other. If there any row who is not independent, then it will automatically becomes the zero row. For example, if you apply the elementary row operation over here and suppose that the first and second and third row makes the first row, then with the help of elementary row operation, that row will becomes the zero. And if we get the any three non-zeros rows, then these three non-zero rows will becomes the basis of a solution of a homogeneous system. And there is also one important question arise, like for a zero vector space. We know that zero is also a vector space because it's independent and it span the zero, a single element can span with itself. Now, this zero vector space has no basis because there is no basis for that because it have only the one element zero which is itself. So it's not need any basis because any subset contains that zero vector must be linearly dependent. Now here there is another important example. We can find the basis of any finite dimensional vector space. Here in this course we are dealing with the problems of a finite dimensional vector spaces. So U is a vector space or subspace of R5 where we have x, y, x plus y, x minus y, and 2. And if we want to find its basis, what we need to do is just like write its vector in a vertical form or in a column vector x, y, x plus y, x minus y, and 2x, and then split the x vector in one side plus y in the separable side, and then you can see that x is common in the first vector, then the rest of vector is 1 0 1 1 2, and plus y if you take common, then the second element is 0 1 1 minus 1 0. Now for all values of x y, look, it means that these two are independent, like the components of the vector with having x and the vector with having y are independent to each other. And moreover, with the help of this linear combination, it generates all the vectors of that form which are in U. So it means these two vectors spans the vectors of a U, and these two are independent to each other. Hence, we conclude that the 1 0 1 1 2 and the 0 1 1 minus 1 0 is the basis for U, for vector space U. Similarly, in the another problem, find a basis for a vector space V, x 1, x2, x3, x4, x5, where x1 is equal to 3, x2, and x3 is the 7 times x4. Now here we can write x1, x2, x3, x4, x5, where x1 is equal to 3 times x2 and x3 is equal to the 7 times x4. Now again need to write the split that into the separate form, since here we have x2, x4, and x5. So just write x2 in the one side. If there is no x2 on that, just put the 0 on that entries. And plus also for x4, we have 7x4 and x4 only in the fourth entry. The rest of entries are 0. And similarly, for x5, there is only x5 in the fifth entry of column vector. So just put x5 in this way. And here you can check it that if you add these threes, it will become same this form, same of that form. Now here in the first vector, we can take x2 as a common. From the second vector, we just take as a x4 common, and the next vector we just take x5 common. Then we will get these three vectors which are independent to each other. You can check it that neither of them, if you add first vector and second vector, it will generate the third vector or vice versa. So all these threes are independent, and with the help of these three in its linear combinations, we can generate v1, v2, v3, v4, v5, where v1 is the 3 times x2 and v3 is the 7 times x4. It means these vectors generates the whole vector space and independent to each other. These From this we conclude that these vectors like 31000 and 017 00710 and from 00001 are the basis elements of the vector space V, or these three is the basis for vector space W. So here there's a one important information regarding that is which is this one, like in R5, like we have a vectors of R5, like these are the 5 tuples vectors. If we have 3 vectors of R5 cannot be the basis for R5, means for R5 the 3 elements are not sufficient to generate the entire vector space, because these threes can be independent, but these 3 cannot span each vector of R5. And if we have 6 vectors, like if there are 6 vectors of R5, then these 6 vectors cannot be becomes a basis for R5, because maybe these can span the whole vector space, but these 6 will not be independent in R5. For R5, they must be exactly 5. So it means that if they are basis, then of a R5, then it must be the 5 vectors. Exactly the 5 vectors should be that. If they are less, than 5 or greater than 5, then they will never become a basis. And there's another one problem, like determine whether we have a polynomial of a degree 2. The basis, we have uh, the three vectors or three polynomials in a P2. So check that is these threes are the basis of P2 or not. Like means are they these three independent to each other, and these three generate every polynomial of P2. For this, just write as a linear combination and then need to find the values of a K1, K2, K3. If the values of K1, K2, K3 is equal to 0 only, then it means they are linearly independent. But here in this case, if you solve, you can see that the values of a K1, K2, and K3s are other than 0. It means they are linearly dependent. If they are linearly dependent, then they will never become a basis for P2. And in the next problem, if S contains the four 2 cross 2 matrices, to determine whether they are basis for M2 cross 2 matrix or not. Again, we need to check that they are independent or not. Just need to find the values of K1, K2, K3. And also there is a method of determinant that if we take the determinant of that one, if determinant is not equal to 0, then it means it have a unique solution, like K1, K2, K3 have only unique solution, which is 0 solution. If there is a unique solution, then it means they are linearly independent. And remember that there is a one good result, like if they are four elements and there are four like of that one, then just need to check that they are independent or not. If they are independent, then these four will also span the whole vector space to a whole vector space of a all M2 cross 2 matrices. And hence we conclude that this becomes the basis for M2 cross 2 matrices. And then there are also some problems regarding the dimension of a vector space. For instance, the all number of elements of a finite basis set is called the dimension of a same vector space V. For example, in Rn, we know that there are like in R3, in the basis elements, there are three vectors, only exactly three vectors. It means the basis of R3 is 3. The basis of a Rn is n. Similarly, the basis of a M2 cross 2 matrices is the 2 multiplied by 2, which is 4. Here we can discuss these things, like if for a finite dimensional vector space, let V1, V2 up to Vn is the basis set, then the set more than that n will becomes linearly dependent. And if we take the fewer elements, then it will not span the vector space V. So these two are the important results regarding that one is. So the dimension of a finite dimensional space V is denoted by the dim of V, mean dimension of V, and it's a positive, or it's a positive number normally, and it's defined the number of vectors in a basis set for V. In addition, the zero vector space is defined have a dimension 0. Remember that the zero vector is only the basis for a zero vector space. So hence we conclude that it has a zero, it has no basis. But in Rn, the dimension is n, mean n vectors will generate the whole vector space. And for polynomial of degree n, we have n plus 1. Why n plus 1? Because in polynomial of degree 2, we have 1x x square. So the constant will generate also for that one. So it means the dimension of a P2 is 3, like 2 plus 1, 3. Similarly, in every polynomial of degree n, the dimension is n plus 1. And for 2 cross 2 matrices, it becomes 2 multiplied by 2, 4. And if we have a M2 cross M of a small m cross n matrices, then its dimension is n times m times n, m multiplied by n. For example, all 2 cross 3 matrices, the dimension is 2 multiplied by 3, which is 6. So we can find the dimension, like first need to find the basis. So we know that how to find the basis, just solve it. the solution space, and then we can see that here it will becomes S and T. When we take S and T common, then we will get the two independent vectors which generate the entire solutions of that one. So these two vectors spans the whole vector space. It means these two vectors are the independent and spanning, so becomes the basis. If they are bases and now v1 and v2 are the only two vectors, it means the dimension of this solution space is 2, because in the basis set there are only the two elements. Similarly, the dimension of a solution space of this one, we need to find its solution, and if we take the common, then we will get v1, v2, v3. There are three vectors which are independent to each other, and then we conclude that these threes are bases, and the dimension is 3 because only the three vectors are in the basis set. So the number of element in the basis set is called a dimension of a that one. So there is also the plus minus theorem. Here you can read it that one, like if S is linearly independent set and V is a vector V that is outside the span of that span of S, then the set S union that vector V is the result by by inserting V into S is still linearly independent. Similarly, we can subtract some vector from that, and then it will becomes again the independent, and we can express as a linear combination of the other vectors in S. Now here we can see its some of its example on that, and so this is the very important result in that direction. Like if V is a n-dimensional vector space and S is a set with exactly n vectors. So dimension is n, and if we have a set which has a n vectors, then S is a basis of V if and only if S span S or S is linearly independent. It means that for example, if you have three vectors for R3, then you need to check that either they are span or are independent. If they are independent, then they must be span, and if they span, then they must be independent, because we know that the bases have only the three vectors. So this is only hold in case we have we know the dimension of a some vector space. Like in Rn, we know that the dimension is n. Similarly, by extraction, we can find the bases, like the bases are independent to each other. So, like if we can see that these vectors are independent to each other, like with the help of like the once we can see that if we multiply any vector with any constant, we cannot get another vector. Then it means both are independent. Or similarly, if we apply its determinant, the determinant will becomes non-zero, which shows the both are independent. Or if we write in a matrices form and apply elementary row operation, we see that both of rows becomes non-zero. It means both are independent to each other. So if they are independent, then it means they are basis of R2. And in R3, here we can check that are these are linearly independent or not. So we can see that either we can apply the determinant, or we can see any form of its that, like apply the elementary operation and just write it in the calling form. You can see that the determinant, the all these three rows are non-zero. It means these threes are the basis of R3. Yes. So here there is a result that if S spans V, and but it's not a basis for V, then it can be reduced to the basis for V by removing appropriate vectors from S. Like we can delete the vector which will become zero in elementary operation, and then the rest of the others will becomes the basis for a vector space. And if S is linearly independent set that is not already basis for V, then S can be enlarged for the basis of V by inserting appropriate vectors, which is independent from the previous vector, and that can generate the entire vector space. And here in this result, we can see that if V is a vector space of a finite dimensional vector space and V is finite, then W is finite dimensional. If W is a finite dimensional, then dimension of W is always less than dimension of V, because V is a vector space and W is a subspace. So dimension of subspace is always less than dimension of V. And if the both are equal, then their dimension will always be equal. So here there are some of the forms of their another results, but the important thing is that we need to know that how to find the basis of a vector space. Like the bases are the independent, bases are always independent to each other, and bases will always generate the whole vector space. And here, if we discuss or we can see some examples of a some of the results, like find a coordinate vector v uh, relative to the basis set of that one. So we can find the coordinate vector of v just like write as a linear combination. Then need to find the values of c, like just take v is equal to c1 v1 plus c2 v2. Then you can find the values of c1 c2, and that will gives us a coordinate vector of v that is denoted with v, and in v and after the bracket there is small s. So similarly for this v, where v is any vector having a b, where a and b's are any real numbers, just write v is equal to c1 v1 plus c2 v2. Then need to find the values of c1 and c2. If you write c1 c2 into the as a vector form, that vector is called the coordinate vector of v. The next thing is that let u and b the b and 2 are the two subspaces of a R5 defined by u is equal to x1, x2, x3, x4 is equal to this one. Then find the basis of u and v. Then we can find the basis of a u and v with the help of the, like we know that we can just write this into the columns form, and then we can apply this to get the result for this one. And in the next problem, determine whether the following form a basis for P2. So for this, determine whether the following. So for that, you just need to check that all these things are independent or not, and span the and all vectors of P2. And in the final problem, find the basis and dimension of a homogeneous system. So we know that if we solve this one, and then we see the solution space, and in the solution space, how many vectors are there that generate the solutions of that one. And if the number of elements are supposed to, then the dimension will becomes 2. In this way, we can find the basis and dimensions. And we already discussed this one in our today's session. Now, students, if you have any question, you can ask your question. Is there any question from your side?
I don't think we have questions, sir.
Okay, fine. But this is very interesting and important topic. I just tell to you that please just see on this important topic, and it will gives you a lot of good knowledge, because it's very interesting and it have a also the variety of its applications. Okay, if there is no question, then we can stop the session now over here. Okay, best wishes for you, and if you have any question, you can just write me. Okay, goodbye.
Hi, Professor. Thank you.